this is a second part of my renal physio. The first part I've done during the primary and MCI refresher course in Hospital Ampang on the 19th. So we're going to continue today with the second part of it. I've already talked all the way until tubular reabsorption and secretion of sodium and potassium. And glomerular filtration has been covered, and auto-regulation and functional anatomy also has been covered. I've shared the link for the course recording from the Ampang, so you all can watch that. But I had a few people who did not attend the course requested me to go through the tubular reabsorption and secretion of electrolytes again. So I'll run through again on sodium and potassium before we go into other electrolytes and countercurrent, and finally with urea and glucose. So we're gonna skip all this. Just this picture, just remember your nephrons in real life does not look like this. Okay, it's not in this order. I want you to remember that it looks like this. Okay, this is your glomerulus and it is in near close proximity with your DCT, distal convoluted tubule. This is your distal tubule, this is your glomerulus. It's not here is your glomerular PCT and DCT is far away. No, it's not like that. Okay, that is very important because again, you see, this is your glomerulus, then is your PCT from proximal convoluted tubule, descending limb of thin loop of Henle, then ascending thick loop of Henle, then is your DCT, distal convoluted tubule, which is in close proximity with your glomerulus and efferent and afferent arterioles. Okay, remember that we have went through all this. I'm going to skip all this at the moment. Okay, so we come to the tubular reabsorption and thing. As a run through, you can look at it. Many of the electrolytes and substances are being filtered. Okay, what are the substances being filtered and what are the substances cannot be filtered? There are few factors toward it. They are charged, their molecular size and everything. Any molecule less than 4 nanometer will get freely filtered. 4 to 8 nanometer is the borderline. More than 8 nanometers are not freely filtered across the glomerulus. And proximal convoluted tubule is a major role in reabsorption of most solutes and also water, including all the electrolytes and nutrients. And most of the time there are secretion and reabsorption. So what are being secreted in PCT is your hydrogen ion along with buffered by your ammonium and your phosphate. And what is being reabsorbed is your sodium, chloride, potassium, water, bicarbonate, and most of the nutrients. Then we followed by your limb of your loop of Henle, which has descending and ascending link, which has different permeability to water. Your descending limb is permeable to solutes and water, whereas your ascending is only permeable to solutes, not permeable to water. So only solutes are being reabsorbed. Then we go to distal convoluted tubule F, which is specific mechanism and more channels, which plays very important part in potassium and hydrogen ion and also regulated by many hormones. So here again, sodium chloride reabsorption occurs, water reabsorption occurs, and then there is a secretion of potassium and hydrogen ions occurs here as well. And then there is role of aldosterone, there is a role of parathyroid hormone for calcium, and all this plays a role here. Then we come to collecting duct, where it has a reabsorption capacity of sodium chloride, urea, and water in the presence of ADH. Okay, this is important for you to know. So glomerular filtration is 1 to 5 ml per day, which is 180 liter per day, but it's only 1% excreted as urine, which is 1.8 liter for a normal person. So we're going to skip this part. This is all theory. I've went through it. Tubular glomerular feedback. No, please watch the other video to have explained this, all this there. We go to the core of the topic today, the second part of it. Okay, tubular reabsorption. So 99% of the glomerular filtrate get reabsorbed. As I mentioned, under 80 liter filtered, only 1.8 liter appears as urine, remaining are reabsorbed. Percentage of water reabsorption may differ from percentage of solute reabsorption. Volume of water excreted may vary without affecting the total solute load. As an example, if every day 5 liters of water being excreted and 500 moles of electrolyte are being excreted as well. But when there is increase in water, increase in volume, the volume of water get excreted may increase without affecting the total solute load. Means 500 mil, only the 500 mil constant value of the solute will get excreted. This depends on the homeostasis of the electrolyte. So in proximal tubule, 60 to 70% of water and sodium reabsorbed. This is the major portion of the sodium and water reabsorption occurs in the nephron. Many substances are transported out in the proximal tubules. It means many get reabsorbed as well. Tubular fluid remain essentially isoosmotic as water moves passively out. At proximal tubule, the main mechanism is solvent drag. Okay, there is large amount of sodium being reabsorbed together with water. This causes a drag mechanism as a solvent drag for many other solutes as in glucose, amino acid, urea as well. So this is where mostly moves passively out down the concentration gradient, either mostly via paracellular diffusion between the cells, paracellular. Okay, we go to the first electrolyte, sodium. Sodium reabsorption occurs mainly in PCT, as we have mentioned. So 60 to 70% get absorbed in proper movement into the tubular cell via co-transporter. How do they act? From the tubular lumen? The filtrate is in the tubular lumen. From the tubular lumen into the cell via sodium potassium ATPase pump. Okay, so we have a tubular lumen, we have a cell, and then we have the cell have a apical membrane which is nearer to the tubular lumen. You have a basolateral membrane which is nearer to your blood capillary. So what maintains the concentration gradient in the cell for the movement of sodium across it? It's the sodium potassium ATPase pump. Okay, the sodium potassium ATPase pump maintains a concentration gradient in the tubule in such as the tubule has a higher concentration gradient, so it can move diffuse back into your blood capillaries. So that is what is meant here. We'll go into it in detail. Just remember this statement. And then from the capillary, from the cells into the capillaries is via Starling forces. So proximal tubule has this sodium hydrogen exchanger. I will come into it. Then in the loop of Henle, it involves sodium chloride and potassium co-transporter, and distal tubule is sodium chloride co-transporter. This is also called a symporter. So in proximal tubule, it is sodium hydrogen exchanger. In loop of Henle, it is sodium 2-chloride potassium symporter or co-transporter. In distal tubule is sodium chloride co-transporter. For all these to occur, the gradient within the cell has to be maintained via an active mechanism, which is the sodium potassium ATPase pump. This movement using this transporter is passive down the concentration gradient, but for this transporter to work, the energy that being driven is come from this sodium potassium ATPase pump, which maintains the concentration gradient within the cell. Sodium is actively transported out of all parts except thin limb of loop of Henle. Okay, except this part where it just goes down out of concentration gradient. 80% of the renal oxygen consumption used to drive this activity, to drive this sodium potassium ATPase pump. So sodium handling in the nephron. So now we go into details of it. That's just an overview. So we know 65 to 75% from the proximal convoluted tubule, another 25% from thin ascending limb of loop of Henle, and another 5 to 10% from the distal convoluted tubule. So in proximal tubule, as I mentioned, the main exchanger that works here is sodium hydrogen exchanger. But for this sodium hydrogen exchanger to work, we need a sodium potassium ATPase pump to maintain this concentration gradient. So what does this sodium potassium ATPase pump do? It pumps out your sodium from the cells into your capillary, and the capillary moves the sodium away from here. It maintains the concentration by flowing away. So this is a active reabsorption, whereas during this potassium goes in here. So when the sodium concentration is kept low in cells, this drives this sodium potassium exchanger down the concentration gradient, sodium hydrogen exchanger. Sodium is being reabsorbed for every hydrogen is being excreted. So why is it important? This mechanism also helps in your acid-base balance to bring down the acidosis, to bring down your hydrogen ion. We come into it later again. So just now, for now, just concentrate on the sodium reabsorption. So sodium potassium ATPase pumps out sodium across the concentration gradient into the capillary using energy, that maintaining the lower concentration in the cells. Sodium from the tubular lumen, which is being filtered, is now being reabsorbed down the concentration gradient in exchange for hydrogen ion, in which this hydrogen ion being excreted as a acid-base balance, okay, by carbonic anhydrase enzyme. When for every hydrogen ion being excreted, bicarb is being reabsorbed together with sodium. So there is two important. One is sodium being reabsorbed from the lumen into the cell, and from the cell it is co-transported with bicarb into the capillary. So sodium reabsorption here occurs down the concentration gradient using this exchanger and symporter, and active reabsorption using sodium potassium ATPase pump. This acid-base balance using which involves the hydrogen ion will come into it later. So remember this part. So there is antipod. So antipod is your sodium hydrogen exchanger and your sodium potassium ATPase pump, and also the chloride, this electrical gradient. Just now we talk about chemical gradient, which is the concentration, and to maintain the electrical gradient, as in because bicarb is being absorbed, to maintain the anion electrical gradient, chloride also being reabsorbed here as well. Okay, so this is to maintain the electrical and chemical gradient. So there is an antipod of sodium hydrogen, chloride and base, and sodium potassium, whereas there is sympod, in which this energy that causes this chemical gradient to be maintained in the cell bring along a lot of other nutrients together with your sodium, as in sodium and glucose. Sodium brings your amino acid, it brings down phosphate, and also brings organic acid together. So many solutes are being reabsorbed together with sodium reabsorption in proximal convoluted tubule. So reabsorption of sodium in thick ascending loop of Henle, this part. Okay, now we are going to this part, thick ascending limb of loop of Henle. So the active reabsorption occurs again. The active means it requires the sodium potassium ATPase pump to maintain the chemical gradient. But the reabsorption from the lumen into the cell is passive. But for this passive diffusion to occur down the concentration gradient using a symporter, the chemical gradient has to be maintained via the sodium potassium ATPase pump, where it uses energy. That's why it's called active reabsorption, secondary active transport. So sodium potassium ATPase pump located in the basolateral membrane. This is the basolateral membrane. Okay, excretes sodium, okay, into the interstitium and leads to low intracellular sodium concentration. It maintains a low chemical gradient of sodium. Sodium potassium 2Cl transporter reabsorb these three solutes down your concentration gradient. To maintain the potassium gradient lower, because the sodium potassium ATPase pump pumps in your potassium here. Potassium will be very high concentration, then the symporter cannot work. So there is a potassium channel in the apical membrane which diffuses back the potassium into the lumen, maintaining a low potassium gradient as well here. Same goes to a chloride channel here, which also reabsorb chloride via passive diffusion down the concentration gradient, thus maintaining a low concentration gradient of chloride. So sodium potassium ATPase pump keeps the sodium concentration low here. The potassium channel, by diffusing back the potassium into the lumen, maintaining a low potassium concentration, and the chloride channel in the basolateral membrane by reabsorption of chloride, it maintains a low chloride concentration. Thus, this importer will passively diffuse these three solutes down the concentration gradient. The chloride move into interstitium via this chloride potassium importer channels as well. Remember, thick ascending loop of Henle is not permeable to water. So water is not being reabsorbed in this thick ascending loop of Henle. So next we go into sodium reabsorption in the distal tubule and collecting duct. As I mentioned, distal tubule and collecting duct are major portion. They play a major portion in your potassium, and they also potassium secretion, and they have highly regulated by many hormones. So what happens in distal tubule and collecting duct? So again, in distal tubule, it's mainly sodium and chloride co-transporter or symporter. Again, the chemical gradient is maintained by the sodium potassium ATPase pump in the basolateral membrane. Low sodium concentration here, thus sodium is being reabsorbed. Chloride also low concentration, so chloride comes together with your sodium. So the concentration of potassium inside the cells, distal tubular cells, are very high. So how does this potassium is being excreted? So that's where the principal cells. There are two cells in your distal tubule. It's called principal cell and intercalated cell. We will talk about in detail when we are talking about potassium handling in kidney. Okay. So sodium, when the potassium is in high concentration here, this is where your aldosterone comes into play. Simply said, aldosterone has two functions. Sodium and water reabsorption. It reabsorbs sodium, it reabsorbs water, so it retains sodium and volume. Okay, it retains water, it retains salt. Retain salt and water, so increase your effective circulating volume. And it secretes, lose the potassium. So this aldosterone will cause stimulation of the sodium potassium ATPase pump, thus reabsorbing the sodium and pushing out the potassium from the capillary into the principal cells. And they also stimulate this epithelial sodium channel, ENAC will come into it, which causes reabsorption of sodium from the lumen into the principal cell, and they also stimulate potassium excretion via this potassium channel. So early distal tubule, we're going to repeat. So active reabsorption of your chloride, sodium and chloride occurs here based on the concentration gradient. The apical membrane contains sodium and chloride symporter. Sodium is pumped out by sodium potassium ATPase, and chloride diffuses into the interstitial cell via the chloride channel. Water is not reabsorbed. The early part of the distal tubule works as the same as your thick limb of descending limb of loop of Henle, where they are impermeable to water. Late distal tubule works same like cortical collecting duct. They have two major types of cells, reabsorptive function, principal cell and intercalated cells. So in which these principal cells, they involve in reabsorption of sodium chloride and water and excretion of potassium, whereas your intercalated cell involved in sodium and potassium exchanger. So what does in principal cell? We talked about it just now. The aldosterone stimulate your sodium channel, stimulate your sodium potassium ATPase pump, increasing the reabsorption of sodium and increasing the secretion of potassium. And aldosterone also stimulate this potassium channel into the apical membrane and into the tubular lumen to be excreted out. Okay. So now we have talked about sodium. So in summary, again, sodium in your proximal tubule, it is sodium hydrogen exchanger, and sodium brings together a lot of solutes together with it. And in limb of loop of Henle, in your thick limb of loop of Henle, it is sodium chloride potassium transporter or symporter, and in distal tubule is sodium chloride co-transporter. All of these need sodium potassium ATPase pump to maintain the chemical gradient within the cell. So this exchanger or symporter can move down the concentration gradient of sodium. So that's being said, now we move on to potassium handling. Potassium is a small cation. So cations are easily filtered across the glomerulus. So it is freely filtered, 100% freely filtered, and reabsorbed 80% in your proximal tubule, around 10% in thick ascending limb of loop of Henle, and then another 10% is depends on the sodium concentration, potassium concentration, where it will be either secreted from 20 to 80, under 80% in collecting tubule and collecting duct, or it is get excreted based on the serum potassium level. So in PCT, 80% is reabsorbed by solvent drag, as I mentioned earlier. It is solvent drag with sodium and water via a paracellular mechanism. Just now I think this is the paracellular mechanism. What we meant by paracellular is between the cells. This is paracellular. Okay, this paracellular mechanism is 100% diffusion down the concentration gradient. So it is reabsorbed in PCT 80% via a solvent drag mechanism with sodium and water. It is via a paracellular diffusion down concentration gradient. In ascending limb of loop of Henle, thick part of it, another 10% is reabsorbed using a secondary active transport, which is sodium, potassium, 2 chlorides in water. We've talked about the mechanism. So here is sodium, chloride, potassium, symporter. And then in distal tubule and collecting duct, the sodium is mainly secreted. The arrow down here means it's secreted. This is reabsorbed. This is reabsorbed. This is secreted. Okay. It is being secreted into the tubule. It means it is highly regulated by your aldosterone. Okay. It is potassium diet, aldosterone or acid limits. It means high serum potassium causes secretion of potassium, mean we are losing potassium. Okay, and also works in your also depends on your medullary collecting duct where it reabsorb potassium. So it is aldosterone regulated. In collecting duct, it is being exchanged for sodium. It is being excreted or reabsorbed based on the serum potassium. If you're able to mention at least this in your SAQ, you will get at least 3 marker, as this contain all the important points. If you are able to say this, if there's a question come out, write a short note on potassium handling on kidney. If you're able to say this much info, you will at least, I think, minimum 2 marks you can get out of the 3 marks. Okay. So now we go into a bit in depth about it. So normal determinants, it's based on the rate of potassium filtration is based on GFR times serum potassium level. If your serum potassium level is higher, more potassium will get filtered. Okay, it's just a direct proportional. Rate of K plus reabsorption depends on the tubules, and rate plus K plus excretion is by the tubule. This is proximal tubule. This is distal tubule. Reabsorption is in the proximal part of the nephron. Secretion is in the distal part of the nephron. So increase in potassium intake, increase in serum potassium, increased potassium will be filtered in glomerulus and go through your cortical collecting tubule, and increased potassium will get excreted under the regulation of your aldosterone, because high serum potassium is a trigger for increased aldosterone secretion. Hyponatremia or hyperkalemia, both of these are stimulus for aldosterone secretion from your adrenal gland. So when there is a high potassium diet compared to a low potassium diet and a normal potassium diet, you can see the secretion is directly proportional. When there is a high potassium diet, your potassium secretion increases directly as a linear. In a normal potassium diet, it goes along with your tubular flow rate. So it's mainly handled by, the potassium excretion is mainly handled by principal cells in your DCT and collecting duct, which is regulation is aldosterone regulated, and there are intercollected cells which have type A and type B. Type A reabsorbs, type B secretes. Okay, type A reabsorbs potassium, type B secretes potassium. We come into it now. So when you look at principal cells first, this is principal cells in distal tubule and collecting tubule. Okay, distal convoluted tubule and collecting tubule. We have a principal cell. This is your basolateral membrane. This is your apical membrane. Okay, this is your blood. It is being reabsorbed into the blood. Okay, this is your tubular lumen. It means whatever going here will get excreted in the urine. This part. This is apical. This is your basolateral membrane. So we can see here in your apical membrane, there is a epithelial sodium channel. This is the sodium channel that I said earlier, which is regulated by aldosterone, which reabsorbs sodium. Aldosterone also will stimulate excretion of potassium via this ROMK, which is called renal outer medullary potassium channel. So aldosterone increases secretion of potassium via stimulating this ROMK and increases reabsorption of sodium by stimulating this ENAC. And aldosterone also upregulate the sodium potassium pump to maintain this chemical gradient. Until late stages of CKD, plasma concentration of sodium is regulated by upregulating sodium potassium ATPase pump, mainly by upregulating this. This is about principal cell. What do their principal cells do? They involve in sodium reabsorption, they involve in potassium excretion, and they are largely regulated via aldosterone influence. That's about principal cell in distal tubule and collecting tubule. Now we go to intercalated cell. Intercalated cell have type A and type B. What does type A do? Type A reabsorbs potassium and type B secrete potassium. Okay, type A reabsorb potassium, type B secrete potassium. Why? How do they do that? Via a potassium hydrogen exchanger. Okay, for every potassium being reabsorbed and hydrogen ion being excreted into the lumen and going into the urine, where every potassium being reabsorbed, every potassium hydrogen ion being reabsorbed, potassium being excreted. It means you can see this is in acidosis, this is in alkalosis. When there is acidosis, there is excess hydrogen ion in the body. The body will try to secrete hydrogen ion and K plus will get reabsorbed. That's why you get hyperkalemia. In terms of alkalosis, we'll try to retain sodium and we will excrete bicarb. So you see there is another symptom on either part of it, which is excrete or reabsorb bicarb. So this is how this intercalated cell plays an important role in acid-base balance. So we come into it. So now we look at type A first. We talked about type A being reabsorbing the potassium and secreting the hydrogen ion in exchange of reabsorbing bicarbonate as well. So look at tubular lumen. This is your apical. This is your basolateral membrane. Okay, so your H2CO3 breaks down into bicarbonate and hydrogen ion. Hydrogen ion is being excreted. Okay, or hydrogen ion, this is moving down the concentration gradient via ATP based transporter channel, or hydrogen ion being excreted via a sodium potassium exchanger. Okay, this is energy driven. Hydrogen ion being excreted, potassium being reabsorbed. This potassium moves down the concentration gradient and get reabsorbed via a potassium channel. And this potassium, when it moves and there is a bicarb extra, this bicarb get reabsorbed and chloride comes in to maintain the electrical gradient. This is anion to anion to maintain base to base. So this is all about chemical and electrical gradient. This is type A intercalated cell. When we talk about type B intercalated cell, it's just the opposite of it. You have too little hydrogen ion, so you want to reabsorb the hydrogen ion. So these channels switch their places. From the apical membrane, they goes into basolateral membrane and they do a opposite function. That's all about it. So in type B, what does it do? It comes into play when you have metabolic alkalosis. So it push out your bicarb, retain your sodium, retain your hydrogen. When you want to retain your hydrogen, you have to secrete your potassium because potassium hydrogen exchanger is here. So that is about intercalated cells. As a summary, what happens in PCT? This is in PCT, potassium handling. Potassium is being reabsorbed via paracellular diffusion. So this is potassium. Follow my arrow. Potassium is being down through a paracellular, between the cell, paracellular diffusion, down the concentration gradient. Okay. How do they maintain the concentration gradient? Via doing there is a sodium hydrogen exchanger and maintaining the sodium potassium ATPase pump and everything. So it goes down the concentration gradient. Then we talk about sodium potassium 2Cl importer. So in PCT, it's paracellular diffusion down concentration gradient. Enough. PCT is 60 to 70% being reabsorbed, which is via paracellular diffusion, down concentration gradient, down. Then we go to thick ascending limb of loop of Henle, where potassium is being reabsorbed via potassium sodium 2 chloride symporter. Okay, potassium 2 chloride symporter. And then we talk about distal tubule and collecting tubule, where the sodium and potassium reabsorption and excretion is variable based on the aldosterone and which cell is involved, either principal cell or type A intercalated cell. Principal cell involved in only in excretion. It excrete sodium, excrete potassium, and it reabsorb sodium. Aldosterone reabsorb sodium, excrete the potassium. Whereas in type A intercalated cell, your potassium is being reabsorbed. Only in metabolic alkalosis, your type B comes into play. So here in potassium hydrogen exchanger, the potassium is reabsorbed, hydrogen is excreted. To make a summary, when there is sodium, potassium and hydrogen, the winner is always sodium. Sodium always get reabsorbed. The one that always lose is hydrogen ion. So when there is sodium and potassium, sodium wins. But when there is potassium and hydrogen, potassium win, hydrogen lose. This is in normal time. In normally, sodium and potassium are being reabsorbed most of the time, and hydrogen ions are being excreted. Okay. This one, I'm just not going to go through it. This is an important question, important points for MCQ. Last time MTF, they asked very frequently, what are the factors that increase your potassium excretion or reduce your potassium excretion? So I'll just leave the slide here. You all can look at it later. It's just basically whatever I've spoken earlier is just put it in the point form. So again, this one I went through again as well. What happens in hyperkalemia and hypokalemia? So in hyperkalemia, it is a stimulus for your aldosterone secretion to push up more potassium out of your body. And in hypokalemia, the aldosterone reduced, so less potassium being excreted. In acidosis, it will cause reabsorption because type A intercalated cell wanted to pump out hydrogen ion. In exchange, they will reabsorb the potassium, causing hyperkalemia, acidosis, the increase in potassium level in your body. In alkalosis, it's the opposite. So type B intercalated cells will come into play, whereas your H plus is being reabsorbed, potassium is being excreted. In acidosis, that's why you see hyperkalemia. In alkalosis, that's why you see hypokalemia. So potassium hydrogen ion in acid base, this is the same thing I've spoken earlier in a different format. You can see for in acidosis, type A intercalated cell, hydrogen ion is being excreted via a potassium hydrogen exchanger and another mechanism via a sodium importer. And then for every hydrogen ion being excreted, bicarb is being reabsorbed, and then potassium being reabsorbed as well, causing hyperkalemia. Whereas in alkalosis, type B intercalated cell comes into play, where hydrogen ion is being reabsorbed, bicarb is being excreted, and then for every hydrogen ion being reabsorbed, potassium in exchanger get excreted. So that's causing hypokalemia. So we have talked about hydrogen ion a lot here. I didn't go into a specific topic, hydrogen ion handling in kidney, because hydrogen ion is involved in sodium hydrogen exchanger and sodium reabsorption. They already involved in bicarb reabsorption. They already involved in potassium handling. So hydrogen is always getting excreted into the lumen of the tubules. So basically, the hydrogen ion concentration in the lumen will be very high. So how do they maintain the chemical gradient of hydrogen ion here? How do they maintain low concentration of hydrogen ion here? So more hydrogen can be pushed out against the pushed out. If the concentration of hydrogen ion is maintained higher, because always hydrogen getting pushed out, more hydrogen ion cannot come out because against the concentration gradient. Okay, even the exchanger will have difficulties to push out. So how do the tubules of your nephron maintain low concentration of hydrogen ion so hydrogen ion can be kept constantly being excreted out. That's where the buffer come into play. What are the important buffers? Your ammonium and phosphate. So when you have acidosis, increase in hydrogen ion in your body, which let's say is respiratory acidosis, you've got increase in CO2. So CO2 will diffuse through, CO2 is very high solubility, easily can diffuse through from your blood into your nephron cells, and it bind with your water and facilitated by carbonic anhydrase, it forms H2CO3 and then broken down into H plus and bicarb. So bicarb will get reabsorbed to buffer your respiratory acidosis, and H plus will get excreted. The H plus get excreted, they will be buffered by two buffers. One is ammonium, which is excess H plus is excreted, high hydrogen ion in tubular fluid. H plus is buffered by NH3. NH3 plus H plus is NH4 plus, and they are buffered by phosphate. HPO4 2 minus plus H plus H2PO4 minus. So these get excreted. So by being buffered, there is no more free hydrogen ion in the tubular lumen. Thus, the concentration of free hydrogen ion is reduced. More hydrogen can be pushed out. So that is the importance of buffers. So free H plus concentration gradient maintained across the lumen, facilitating more hydrogen ion excretion. This if they ask you about how do renal acid-base role of renal, kidneys role in acid-base balance. So you have to kind of intermerge all these things to talk about it. It is mainly hydrogen ion which works in your PCT, works in your DCT. In PCT is proximal convoluted tubule is sodium hydrogen exchanger. Here is potassium hydrogen exchanger. The one that remove hydrogen ion is your type A intercalated cell. The one that retain your hydrogen ion is type B intercalated cell. For every hydrogen ion being excreted, bicarb being reabsorbed, potassium being reabsorbed. For every hydrogen ion being retained, one bicarb being loose and potassium being loose. So this is a summary of renal handling of potassium. So now we go to calcium, magnesium and phosphate. So again, what is paracellular? Paracellular is in between. Transcellular is directly going through the cell via a certain channel or symporter. Just give me a moment. My patient is not stable. Okay, we continue. So calcium handling, again PCT, thick ascending loop of Henle and DCT. Exactly follow sodium. Calcium follows sodium. The highest amount is being absorbed in PCT, 60 to 70%, same like your sodium. 20 to 25% in thick ascending loop of Henle, same like sodium. Another 10% in distal convoluted tubule, same like sodium. But here they have a paracellular and transcellular mechanism, almost similar to sodium as well. But sodium has this potassium, sodium-potassium ATPase pump to maintain the concentration gradient. But here the sodium-potassium ATPase pump maintains the electrical gradient. We come into it. So total body calcium is 98%, which is bound in bone. Only 2% exits freely in your intracellular and ECF. From the ECF of the 2% is freely filtered because cations are easily filtered in your glomerulus. Out of the freely filtered, 99% is reabsorbed, almost exactly same like your sodium as well. So it works by a paracellular mechanism in PCT and thick ascending limb of loop of Henle, whereas transcellular in distal convoluted tubule and collecting tubule. So 60 to 70% and 20 to 25% in earlier part of the nephron by paracellular is down concentration gradient, not regulated by any hormone, whereas in transcellular mechanism in the distal part is parathyroid hormone regulated. Your calcium phosphate homeostasis are very closely regulated by your parathyroid hormone. We come into it. So in proximal tubule, what happens? Paracellular diffusion between the cell, paracellular diffusion. It works by a chemical gradient which is maintained by sodium and water reabsorption. When a lot of water being reabsorbed and sodium being reabsorbed here, the chemical gradient of sodium is very low here. Means the cation concentration gradient is low here, and also chloride concentration gradient. Chloride maintains the electrical gradient. So you just have to mention in proximal tubule, calcium is reabsorbed via paracellular diffusion, in which the chemical gradient is maintained via sodium and water reabsorption, and electrical gradient is maintained via chloride reabsorption. If you can mention this, more than enough. 60 to 70% reabsorbed in PCT via paracellular diffusion, in which the concentration and electrical gradient maintained by sodium and water reabsorption and chloride reabsorption respectively. Next, we talk about thick ascending limb of loop of Henle, where your calcium reabsorption again is paracellular diffusion. Here, the electrical gradient is maintained via potassium recycling. So if you look at it, if you look at the sodium potassium ATPase pump, it pumps in a lot of potassium into the cell. The potassium concentration is very high here. So the potassium have to leak through this ROMK channel to maintain a low concentration gradient. So this importer can work. So this importer maintain the electrical gradient of potassium here, that maintains your drives the calcium reabsorption via paracellular diffusion. Don't overthink all this much. Calcium phosphate handling all will come in a very small questions only. If you're able to say this much, is more than enough. Then distal convoluted tubule, where you have a specific mechanism and specific channels. It works via a transcellular mechanism involving few channels, in which in apical, this is your apical, this is your basolateral membrane. Apical, you have a specific channel as TRPV5 apical channel. If you cannot remember, you can just apical calcium channel, where it transports calcium down the concentration gradient, and from the cell into the blood at the basolateral membrane, you have sodium calcium exchanger. This is sodium calcium exchanger. Okay. Here the sodium is being pumped out. Here sodium is being pumped in. This is the exchanger, and sodium calcium ATPase pump. So this is calcium ATPase pump. Okay. This is energy driven calcium pump. So in apical, you have a special channel to reabsorb the calcium. From the cells into your blood at the basolateral membrane, you have a sodium calcium exchanger and you have a calcium ATPase pump. So you have to able to mention this is more than enough. That's about calcium handling. Summary, if you find it difficult to remember this, I'm just going to give you this. If you can memorize this and write, you will get full mark for sure. Freely filtered, 99% reabsorb. Out of the 99 reabsorb, it works by paracellular and transcellular. 70% at the PCT reabsorbed with sodium, driven by a chemical gradient, sodium water, and electrical gradient, chloride. At 15% at thick ascending limb of loop of Henle, driven by electrical gradient, driven by potassium recycling. Transcellular 15% DCT and VCT via special channels that I mentioned, regulated by PTH reabsorption. Phosphate handling, it again, phosphate 85% in the bone, 14% in tissue, and 1% in ECF. Freely filtered again, 85% reabsorbed, all by transcellular mechanism. It goes through the cell, reabsorbed 80% in the proximal convoluted tubule. Okay, another 5% in the distal tubule. The 80% is the most important. It works via sodium phosphate symporter. This importer, again, is the energy, the chemical gradient, which is maintained via the energy driven by the sodium potassium ATPase pump. Low sodium concentration here. So sodium is being brought in by this importer along with the phosphate. And at the basolateral membrane, there is an unknown phosphate anion exchanger where phosphate getting reabsorbed here. This is regulated by PTH. Okay, parathyroid hormone regulate calcium handling where it reabsorbs calcium, where else in phosphate, it is regulates the phosphate handling, but it excretes phosphate. Okay, calcium is being reabsorbed, phosphate is being excreted under the parathyroid hormone influence. Okay, another 5% in DCT and CT. This is much is more than enough for phosphate. So calcium phosphate homeostasis, I'm not going to go into this in depth. You should know this. It comes under endocrine and everything. Your parathyroid hormone has effect on your bone, renal, and bowel. Practically, parathyroid hormone, the work is to increase your serum calcium and reduces your phosphate. So the stimulus for parathyroid hormone release is hypercalcemia. hypocalcemia or hyperphosphatemia. Low calcium or high phosphate stimulate parathyroid hormone. Parathyroid hormone causes calcium resorption. It makes your bone to be osteoporotic. It releases calcium from bone, so serum calcium becomes high. It causes renal reabsorption of calcium. It stimulates your vitamin D, active formation of vitamin D in kidney, where vitamin D increases reabsorption of calcium in your renal and reabsorption of calcium in your gut. Okay, that what does parathyroid hormone does, and it excrete phosphate. What what is the stimulus to reduce the calcium? Is by calcitonin. Calcitonin only acts on your bone. It inhibits the calcium resorption from your bone. It keeps the calcium inside the bone. That is calcitonin. So calcium is regulated by PTH, vitamin D, and calcitonin, where PTH and vitamin D increases the calcium level. Calcitonin reduces your serum calcium level. How does this PTH affects your nephron? I've talked about it earlier, so I'm just going to leave it here, then you all can look at it. How do they know the level of calcium? There's something called calcium sensing receptor, CSR, which is a G protein coupled receptor, highly abundant in kidneys and parathyroid glands. Magnesium handling, it again can be as a very short note, just for completion's sake. Total body magnesium, 50% in bone, another 45 to 48% intracellular, 1 to 2% on extracellular space. This extracellular load, out of 80% from this extracellular will get freely filtered. Above that, 95 to 90% will get reabsorbed, but compared to potassium, sodium, and calcium, magnesium reabsorption is mainly in thick ascending limb. This is the distinguishing feature of magnesium, whereas all the other cations, sodium, potassium, and calcium is PCT, whereas for magnesium it's in thick ascending limb, mostly via a paracellular mechanism. Again, whenever in thick ascending limb, the electrical gradient is from potassium recycling. Another 10% is in the apical magnesium channel. So thick ascending limb, your proximal tubule is passive diffusion paracellular. Okay, passive diffusion paracellular via the solvent drag. In thick ascending limb, also paracellular, but it needs a chemical electrical gradient that is created by the potassium channel. We had talked about it a lot of time. And then finally, in 10% in distal convoluted tubule using a apical magnesium channel, special magnesium channel. In distal convoluted tubule, everything uses special channel. Remember like that. In PCT and ascending limb of loop of Henle, it's all a symporter or cord transporter or exchanger. But in distal convoluted tubule, there will be always some specific channel for specific for cations. So next we go to water transport. So this is water transport is important to explain about how the urine get concentrated. You produce a concentrated urine. So you look at nephrons, the permeability of water. These pictures are just to show the permeability of water. Your permeability of water is very high in your proximal convoluted tubule. Descending limb has considerably good permeability of water, but your ascending limb, the thick ascending limb of loop of Henle is completely impermeable to water. And then your distal and collecting duct, they have variable permeability to water based on the presence of antidiuretic hormone, ADH, or human vasopressin. Is the same thing. So PCT and descending limb have significantly good permeability to water. It means water will get reabsorbed. In ascending thick limb of loop of Henle, there is no permeability to water. There is no water reabsorption. Distal convoluted tubule and collecting duct, they have variable permeability to water and variable reabsorption of water based on the presence of ADH. All this reabsorption of water involve aquaporin channel. Aquaporin, they have 1 to 7 lah. So I'm not going to go into the depth of it. At each different part of the nephron, different type of various type of aquaporin come into play, but you can just mention aquaporin channel. Aquaporin channel get inserted in the apical part or basolateral part. Depends on what type of aquaporin is that. 70% water occurs at your proximal tubule, another 20% at the tin, another 10%. The percentage is almost similar to sodium and calcium, just in difference. 70% in PCT is the same, 10% in distal part is the same, but only this 20% for calcium and sodium is at the ascending limb, whereas for water is in the descending limb. So water transport, proximal tubule 60 to 70% reabsorb. Aquaporin 1 located on basolateral apical membrane. You don't remember the numbers, it's okay. Fluid remains isotonic. Why the fluid remains isotonic? Because along with the water, solutes also majorly getting reabsorbed. Your sodium, potassium, sodium, potassium, magnesium, sodium, potassium, calcium, and your glucose, your amino acid. So there is a solute reabsorption, there is water reabsorption. That's why the fluid remain isotonic. Whereas in loop of Henle, descending limb, the one that goes down, the thin descending limb is permeable to water. So more water get reabsorbed. So it become, the tubular fluid become hypertonic, more concentrated because the water is being reabsorbed. So the medulla become hypotonic here, but here it become hypertonic. Okay. Whereas the ascending limb not permeable to water, sodium, but the solutes can be reabsorbed. Water remains and become hypotonic. So inside here, the tubular fluid, as they go down, they become hypertonic because more water being reabsorbed. Whereas here and the ascending part, more solute being reabsorbed, water is completely impermeable. That water stays in, making it hypotonic. Okay, remember that. So water transport in distal tubule is similar to the ascending limb. Distal, this is the distal tubule, is same like here. Then we talk about the collecting ducts. The collecting duct permeability depends on ADH, where what does ADH do? It causes rapid insertion of aquaporin into the apical membrane. Means it just inserts more aquaporin channel, more water can get reabsorbed. How does this aquaporin channel work? It works via V2 receptor. Okay, the cyclic AMP and protein kinase A. It's all G protein coupled receptors. With ADH, water moves into interstitium, fluid become hypertonic. This is how your urine get concentrated. Let's say you're under volume, hypovolemic, that's the stimulus for your ADH get secreted. What does ADH do? They via a second messenger mechanism, cyclic AMP, they insert aquaporin channel into the apical membrane. More water get reabsorbed from the tubular lumen into the blood capillaries, that the urine that goes out going to be concentrated. Without the ADH, less water get reabsorbed, urine will be diluted. So what is ADH or antidiuretic hormone? It's another name is human vasopressin. Vasopressin is synthetic, that's why we call it human. In our body, vasopressin is called antidiuretic hormone. But we cannot give vasopressin, ADH as in synthetic into patient. That's why what we give is vasopressin in outside. Okay. I'm not going into in detail about ADH and vasopressin here. What does ADH do? It affects increase the permeability of water to the collecting duct, so more water get reabsorbed. So thus it reduces the urine volume, reduces the blood flow through renal medulla. Less blood flow through renal medulla, less GFR, less blood through to cortex, everything like me. It just reduces the GFR, less urine. Increases thirst, increases the water intake, regulate sodium and ECF volume. Basically, it increases your sodium water in your body. As water is retained, more sodium will get retained as well. Regulation is via osmoreceptors, volume receptors, emotion and stress. Where does it secreted from? It's secreted from your pituitary gland. Main stimulus for your secretion is your blood volume and increase in solute concentration. Hypertonic, hypoosmolar serum or hypovolemia. Okay, it's all a stimulation for antidiuretic hormone. ADH, what happens? So when it's ADH or human vasopressin, once they have released, so as vasopressin binds to the membrane receptor. So where is the membrane receptor? Is here in the blood. So vasopressin, so ADH secreted from pituitary gland, it comes to your blood circulation, goes to your kidney. In the blood, it crosses across and it goes to the basolateral membrane part first. So it binds to the basolateral membrane. It binds to the membrane receptor. It activates the cyclic AMP second messenger system. Okay, once the cyclic AMP is get activated, this second messenger system will insert the aquaporin channel in the apical membrane, water get reabsorbed. This much of 4 sentences enough to explain ADH action at the collecting duct. You don't have to mention aquaporin 1, 2, 3, it's never mind. Just make sure you mention the right word at the vasopressin binding to the basolateral membrane receptor, and aquaporin channel is being inserted in the apical membrane and water moves down via the concentration gradient. Okay, it's get reabsorbed with the presence of ADH. So BP and BP flow, blood pressure and your volume control in blood, it's interrelated to your renin, angiotensin, aldosterone system, and your kidney plays an important role in your blood pressure control as well. This is an overview of the whole thing I'm talked about. I think I'm not going to explain this. I found this is very good to explain about how kidney works along with your pituitary, hypothalamus, and your right atrium is your ANP, stretch receptors multiple. I'm going to leave it here. You all get to look at it later. You go through one by one. You can understand the whole blood pressure homeostasis in the blood, including baroreceptors, osmoreceptors, stretch receptors, volume receptors, and what are all the chemicals that involve. I found this in online. I find it very good. So that's why I'm sharing it here. This is just to keep it simple. If you find this is too much to remember and to put it up in your exam, this is the simplified version of it. Okay, hypovolemia, low blood pressure baroreceptors get activated, high pressure baroreceptors get activated. Sympathetic stimulation, vasoconstriction, increase heart. This is low pressure receptors causes release of chemical. This is direct sympathetic stimulation. This is indirectly via the chemicals, ANP, ADH, and your aldosterone. Your renin, angiotensin come into play, sodium and water retention. Here, direct sympathetic stimulation, increasing vasoconstriction, heart rate, and your contractility. This is the much simplified form where what happens in your hypovolemia or in your low blood pressure situation. So renin, angiotensin, aldosterone system, I'm not going to repeat it. Please watch the other video. This is again just for repetition. This is again another good flow chart to explain the whole renin, angiotensin, aldosterone system in one page. If you can understand this, you put it up in your SAQ. If there is a question, write a short answer question on renin, angiotensin, aldosterone system. If you can put it exactly like this in point form without the pictures, no need to draw the pictures. If you can put it in this mind map, you will get full marks for sure. So next we go into the water transport. So water transport is how the urine getting concentrated. So in order to remove more water, you have more water in your body, you want to excrete it, the more water have to be removed from the urine. So urine must be hypotonic, diluted. In order to remove more solutes, let's say your serum is hypoosmolar, it's very thick. So example in diabetes mellitus or DKA, you got so much of sugar in your blood. So you have to remove more solutes from the body. So your urine must be concentrated. Your urine must be hypertonic now. So how do kidney achieve this? In order to make urine hypotonic, it means urine is diluted. Okay, clear urine. More water has to be excreted. So, solute must be removed in excess of water. So ascending limb loop of Henle is impermeable to water, but solutes removed. Okay. Solutes must not be allowed to re-enter the tubule. Sodium still being actively transported. Water must not be allowed to exit the tubule. Collecting ducts is okay. So in order to make the urine hypotonic, sorry, I think there is a typo here. Let me read back again. In order to remove more water than solutes from the body, in order to remove more solutes than water from the body, urine must be hypotonic. Okay, in order to make the urine hypotonic, sorry, this is in order to make the urine, solute must be removed. No, in order to make the urine hypertonic, sorry, if you want to make a concentrated urine, okay. Sorry, okay, let me recap my mistake. Okay, in order to make the urine hypotonic mean you want to produce a diluted urine. Okay, you want to remove more water. Solute must be removed in excess of water initially, where in ascending limb of loop of Henle, your water is impermeable. Okay, so more solute being reabsorbed here. Tubular lumen water is maintained. Solute must be removed, as in solute must be reabsorbed in excess of water from the tubular lumen. When I mentioned removed here, removed from the tubular lumen. So in this part, more solutes being reabsorbed, water must stay inside here, so it can go to the urine and get excreted. Solute must not be allowed to re-enter the tubule. Solute that get reabsorbed here should not go inside here, So that's why in collecting duct, sodium is getting reabsorbed still actively. So the solutes are still getting reabsorbed, water still stay inside. And water must not be allowed to exit tubule. Water in the collecting tubule should not be allowed to come out. So how do they do that? In the absence of ADH. When there is no ADH, water will not get reabsorbed. So just to repeat again, so just to make clarify, how you're going to make a diluted urine? You have to make sure in the thick ascending limb of loop only, water is not being reabsorbed, only solute being reabsorbed. And at the collecting duct, solutes are still being reabsorbed and they are not allowed to solute going back into the tubule, and water is not being reabsorbed because there is no ADH. If there is ADH, water will get reabsorbed. You want to produce a diluted urine, there should not be ADH influence in the collecting tubule. If it's in a order where you want to make a concentrated urine, it's just other way around. This is where your countercurrent mechanism comes into play. Though the interstitium must be made hypertonic. So how do they do? Because of the different permeability of your limb of loop of Henle. I've mentioned your descending limb of loop of Henle is permeable to water, ascending is not, and that's where your countercurrent multiplier. You have a countercurrent mechanism where you have a multiplier and exchanger. Multiplier is the mechanism between limb of loop of Henle and the interstitium. This is the interaction between the tubules and the interstitium. The exchange of water and solute from the tubule into the interstitium, it is countercurrent multiplier. So by doing this and a different permeability of water in the descending and ascending, the medulla become more hypertonic. And water must be allowed to move out of the tubule. This is in the collecting duct, as I mentioned. When there is ADH, more water being reabsorbed, thus the tubular lumen fluid will be very concentrated. Water must be removed from the interstitium. So, okay, a lot of water is being removed from the tubule into the interstitium. There's the interstitium medullary conicity is down. So how to keep it always hypertonic? That's where your countercurrent exchanger comes in, who keeps the medullary tonicity always high. So that is the interaction between your interstitium and vasorecta. So countercurrent multiplier is a interaction between your tubule and interstitium, and countercurrent exchanger is a interaction between your interstitium and vasa recta. Okay, to put in picture. Okay, as I said, this is the simplified. As I said, when you want to talk about nephron, you have to look into vasa recta together. So it is a counter current mechanism, mean the flow is counter. Okay, we have ascending and descending limb of loop of Henle, where descending limb of loop of Henle goes down, the tubular fluid is going down. Your ascending limb of loop of Henle, fluid goes up. Whereas in your vasa recta, the flow is opposite to the loop of Henle. Okay, at the part vasa recta is in near proximity with the ascending limb, the flow goes against, and vice versa for the descending limb. Okay, this is your vasa recta. It goes from like this, whereas a limb of loop of Henle goes like this. So both have ascending and descending limb. Both have solutes and water going in and out. Okay, both vasa recta and limb of loop of Henle both have sodium and water going in and out. In vasa recta, there is no difference in permeability to water and sodium. They always move down the concentration gradient. Whereas in limb of loop of Henle, there is a differential permeability to water. The descending limb is permeable to water and solute, whereas your thick ascending limb is only permeable to solute, is impermeable to water. So that is the important thing that you have to remember. And when you vasa recta, when we talk about the urea role in that, your collecting tubule have urea recycling, where urea will get reabsorbed from the collecting tubule to the interstitium, maintaining the hypertonicity, and water reabsorption from the collecting tubule to decide the medullary hypertonicity here is based on the presence or absence of ADH. So countercurrent multiplier, we talk about multiplier. Multiplier is loop of Henle and interstitium interaction. So loop of Henle and interstitium, this part and this part. So what happened? as tubular fluid moves down the thin descending limb. From the PCT, the fluid comes down here. Okay. We know already many of the solute that is being filtered at the glomerulus already being reabsorbed at the PCT. And water also get reabsorbed. So most of the time, the fluid that comes from PCT is isotonic because equal amount of water and solute being reabsorbed at the PCT. So as they goes down the descending limb, the tubular fluid become more hypertonic because water moves out of the descending limb. The higher the osmolarity of the ECF, the more water leaves the descending limb via the osmosis. Okay. The more water that leaves the descending limb, the saltier the fluid that remains into it. Means the tonicity of the tubular fluid, osmolality of the tubular fluid become increased. From 300, it become 1200 at the tip of the loop, at the hairpin loop of the limb or loop of Henle, 1200 the tubular fluid. Okay. Achieve same tonicity as the medulla. The medulla will be that also. Water removed by vasa recta. So don't think about the vasa recta here. The water that comes out here, it doesn't stay here. To maintain the concentration gradient of low tonicity here, mean low water, the water will always get taken up by the vasa recta because the tubular fluid moves this way, vasa recta goes this way. So water that comes out goes into the vasa recta and bring up into the systemic circulation. It goes out. As the tubular fluid moves up the ascending limb, the thick ascending limb, solute moves out because we know this part is impermeable to water. Impermeable to water, where solute moves out of the tubular fluid into maintain the hypoosmolarity in medulla, whereas water does not. So the hypoosmolar medulla comes out to 1200 to 1400, maintained by balanced inflow and outflow of solutes and water in medulla. Okay, so this part water comes out, this part solutes comes out more. So the tubular fluid become hypertonic as it goes down the limb of loop of Henle, but as they goes up, they become hypotonic because more solutes being pushed out, but water retained in the tubule. So again, this is to look at it again. Look at this first. Don't look at this. Look at this first. As I mentioned, water comes out. The water that comes out is taken away by the vasa recta. Vasa recta. So as here, as they move up, the tubular fluid moves up. The solute that moves out, taken up by the vasa recta. So tubular fluid is hypertonic here. Vasa recta blood is hypertonic here. So it goes down, more solute comes in and it become hypertonic. So here it become hypertonic, but when it goes up here, this hypertonicity draws in fluid from here to come here to reach equilibrium. That's what happened. So it is a counter current flow with differences in tonicity of their fluid, which attracts the movement of solute and water across down the concentration gradient at different flow, at different part of the ascending and descending limb. This much is enough. You're just able to mention the differential permeability of loop of Henle, the counter current flow of loop of Henle and vasa recta, and you are able to draw this simple diagram, this part, and show this is enough. At the tip, the hairpin loop, both of them are hypertonicity, highly tonicity, because this part is the part they reach equilibrium with each other. But as you see, as they move with it, they'll try to reach equilibrium because the solutes move in and out, up and right and left until they reach equilibrium. So that's what happening here. Okay. So the counter current exchanger is the vasa recta. Water moves out and blood becomes more concentrated. So water moves out. This part here, this part, water moves out and blood become more concentrated. Sodium moves in, moves down towards the tip of the medulla. So this part, when I talk about it, the sodium moves in, it become tip of the medulla, become more hypertonic. As blood moves up the vasa recta, water which moved out of the descending limb of loop of Henle and vasa recta moves into the ascending vasa recta. Water is carried out of the medulla water that moves into the vasa recta is being carried away from the limb of loop of Henle because of the continuous flow of your blood flow. Sodium moves out and recirculates in the medulla. Some sodium is carried out by the vasa recta. So you just have to mention the movement of solute in and out. So this is just to put in the whole thing together and leave this picture here. I'm just want to confuse you. This is in putting up the solute and the water transport mechanism in one thing. Though the symptotus, we start from here. The symptotus in the thick ascending limb of causes buildup of sodium and chloride in the renal medulla, because this part, sodium chloride being reabsorbed. So this hypertonicity at the nephron loop, the counter current flow through nephron loop establish the osmotic gradient. We talk about the ascending and descending across flow of your limb of loop of Henle and vasa recta. Then principal cell in collecting duct reabsorb more water when the ADH is present. Urea recycling maintain the buildup of sodium. That's why your concentrated urine is produced. This is just a repetition. You all read this again. I leave it here. So some people want to read in sentences in point form. This is countercurrent mechanism, explaining this in more wordy form. I leave it here. So countercurrent mechanism, this comes out in MCQ. Effect of increasing GFR on your countercurrent mechanism. Effect of increasing medullary blood flow in countercurrent mechanism. I'll leave it here for MCQ purpose. So urea recycling. Briefly, what is the role of urea? Urea maintains the hypertonicity of the medulla. It recirculates between your collecting duct and thin limbs of loop of Henle. Thick limb of loop of Henle is not permeable to urea. Okay, it's same like water. Urea and water shares the same permeability. They are more permeable in thin limbs. They are not permeable, relatively impermeable at the thick limb of lip of Henle. It increases the ability of kidney to concentrate the urine. Hyperosmolarity in the medulla is set up so the fluid flowing down the collecting duct can achieve high concentration. Free water clearance, quantify gain or water loss between. Quantify the gain or loss of water difference between the urine volumes. Okay, this is just in terms of urea, they will talk about free water clearance. Just ignore this, no problem. So urea that is being freely filtered, reabsorb almost 100% here. Okay, urea that being reabsorbed stays in here. Okay, it get reabsorbed in your PCT, some part of it. Okay, then it goes down. Then it goes down all the way here, where it get reabsorbed in your distal collecting tubule. Okay, until in your distal collecting tubule, most of the urea is not being reabsorbed. Your urea is increasing, the concentration getting increase until at the collecting tubule, urea is being permeable, get reabsorbed. The urea that reabsorbed into the interstitial medulla will either goes into the mainly into the thin limb loop of Henle. The thick part of the loop of Henle where it is impermeable. The picture does not show the thin and thick part, but this is the thick part. The yellow part is the impermeable part of the urea. So urea goes in here to maintain the tonicity. Why is it important? When urea moves in the interstitial medullary, the hypertonicity here will draws out water from here, from collecting tubule. Okay. Again, when the urea moves in here, that will draw water from here to come inside here also. Again, you see this water and everything, it is just recycling of urea to maintain the hypertonicity of medulla. Okay, this much of urea recycling is enough. I don't want to explain too much on it lah. Okay, urea recycling is important. Recirculate between the collecting duct and thin limb of Henle. It increases the ability of kidney to concentrate the urine. If you can able to mention the differential permeability of urea at collecting tubule and thin limbs of loop of Henle, similar to your water, is enough. So next we go to glucose handling. Glucose are small polar molecules which are non-protein bound. They are freely filtered in the glomerulus under 80 gram per day. In health, almost 100% of the glucose is reabsorbed in the proximal tubule. That's why you don't see your glucose. When you do a urine FAME, you shouldn't see a glucose unless you are diabetic or you have some kidney disease. Okay. So glucose is being filtered. It's more than 90 to 100%. Almost 100% of it is reabsorbed. In proximal tubule, mostly it reabsorbed 90%. And at the distal part of the proximal tubule, another 10%. Mostly all 99 to 100% of the reabsorption of glucose occurs in the proximal tubule. It's just where is it, at the early part of the proximal tubule or the late part of the proximal tubule. Why is it important? They mentioned because the glucose transporter involved in the early and late part of the proximal tubule is different, SGLT1 and SGLT2. So reabsorption uses a transporter called sodium glucose co-transporter, SGLT, got 1 and 2. So how does SGLT works? Uses the sodium potassium ATPase pump. Again, the sodium pump, because I've talked during the sodium reabsorption. Sodium reabsorbed as a solvent drag, it brings along the many molecules together. One of it is your glucose. Okay, this is your basolateral membrane nearer to the blood. This is your apical membrane nearer to your tubular fluid or urine. Okay, so sodium potassium ATPase pump maintain the concentration gradient of your sodium low in the cells, proximal tubular cells. Thus, sodium moves down the concentration gradient using the SGLT co-transporter, bringing along the glucose with it. And then glucose is reabsorbed from the basolateral membrane into the blood using this is the apical membrane channel. This is your GLUT, GLT, followed by facilitated diffusion using a GLUT transporter, glucose transporter. Okay, the apical membrane as SGLT transporter, which is sodium glucose co-transporter, which brings down glucose along with the sodium down the concentration gradient of sodium, and then from the apical, from the tubular cells into your blood at the basolateral membrane, there is your glucose transporter, which is called GLUT. Facilitated diffusion of glucose occurs via using this glucose transporter. More than enough to mention about glucose handling. Okay. Pictures, sodium potassium ATPase pump, sodium concentration low, sodium comes down, bringing along glucose with it. And then here, this is the SGLT, this is a GLUT. So what importance in glucose handling is when glucose appears in urine. So that is the question that comes in glucose handling as a second part of the question. So this is where you have to draw this graph. It's a very simple graph, X and Y. X-axis, you just mention your plasma glucose. Just put 10, 20, 30 and 40. Do it in a millimole. That's what we do practice. Don't put in milligram per deciliter. You'll get confused. We monitor glucose in our practice, our setting, millimole per liter. So use this millimole per liter. And on the Y-axis, you just put 200, 400 and 600. This is milligram per minute. You can just mention as glucose flux. Glucose flux, renal glucose flux, or what flux mean is the movement in and out. So it is, what is it? Rate of glucose filtration, reabsorption and excretion. In one sentence, you can just mention a rate of glucose flux. Flux mean is in and out. So it involves filtration, reabsorption, excretion. Flux is involved all these things. Means how much is being filtered, how much is being reabsorbed, how much is being secreted or excreted. So that's what we're going to talk. So what happens is until, so this is the glucose flux, okay? We have something called transport maximum, which is 375 milligram per minute. This is the maximum flux of glucose across the transporters, which is your SGLT1 and your GLUT. So your glucose transporters, they have transport maximum where they can only function. That is your max speed lah, max limit. They are saturated beyond that limit. So when your glucose flux is more than 375 milligram per minute, they cannot work anymore. They're saturated, so they cannot reabsorb. So when does this happen? At the renal threshold glucose of 11 millimole per liter. That is why our diabetes mellitus one, your random blood glucose more than level, you consider diabetes. Your fasting blood glucose more than 5.5, and then 7.7 and 11.1, right, which is impact glucose tolerance and then confirm diabetes and everything. Okay, so 11 millimole per liter. Until if your serum glucose is less than 11 millimole per liter, whatever this dashed line is the filtered glucose at your glomerulus. We know everything that glucose that is filtered will get reabsorbed. So if your your serum glucose is 11 millimole and lesser, whatever that being filtered will get reabsorbed. This line, filtered will get reabsorbed. If your renal if your serum glucose is more than 11 millimole per liter, it means the filtrate that comes with your glomerulus as a glucose of more than 11 millimole per liter, the transport maximum is achieved. So beyond that limit, whatever the glucose being filtered will not get reabsorbed because it already meets a plateau. It will get excreted. So the filtration, the excretion of glucose will be in linear with the filtration of glucose beyond a renal threshold of 11 millimole per liter. So if they ask you what is the glucose handling by kidney, when the serum glucose is more than 11 millimole per liter, a renal threshold of 11 millimole per liter will achieved, where in which the transport maximum of say 375 milligram per minute is already achieved. With whatever glucose that being filtered beyond this limit will not get reabsorbed, will get excreted. So you can see this line. Beyond that renal threshold, transport maximum achieved. So whatever being filtered will get excreted. So glucose reabsorptive mechanism is saturable, the SGLT mainly. So plasma glucose more than 11, your glucose will not get reabsorbed. Anything more than 11 will get glycosuria. That's why you get osmotic diuretic like in DKA. Your sugar is too much, it's getting short, and urine is hypertonic, it's dragging together your water with it. That's why patient DKA are dehydrated. You have to give them a lot of fluid. Okay, this is a summary. This is like one of I think when we are in master students, I can't remember which group did it. This is a summary of the whole thing, all the electrolytes and solutes and water, the percentage and where it occurs in simplified form. This you can keep it as a reference sheet, okay, and mentioning about the percentage and what are the channels involved and everything. Just for a quick reference, you can keep it. I will share it. And whenever I'll advise you, once you read renal physio, immediately read about diuretics so you can understand how each diuretics work at different part of the nephron. Don't keep the diuretic topic later. Once you read about the renal physio, immediately the next day go and read about the diuretic. So you'll understand the diuretic topic much more clearer, and you'll understand why this diuretic causes this electrolyte imbalance. How does aldosterone potassium sparing antagonist works? How does spironolactone works? How amiloride works? Why does mannitol causes differences, hypokalemia? Everything you will know. So this is another picture that shows different part of reabsorption along with the diuretic. Renal physiology involved together with the diuretics. You look at this and you read together your diuretics after you understand your renal physio will be much clearer. Okay, this is just a repetition. I don't think we have time to discuss the SAQ practice. I hope everyone have tried it. Next week, I'll do a class to discuss about this SAQ practice. Okay.